Hello everyone, I'm Zheng Jieyang from Tsinghua University. I'm honored to present our work achieving efficient routing in reconfigurable DCNS here. This is a joint work with researchers from Tsinghua University, Huawei Technologies, Stony Brook University, and City University of Hong Kong. We all can see that cloud computing plays an important role in all aspects of our lives. We play cloud games, we listen to cloud music, we collaborate with others with the assistance of cloud computing. Almost everyone knows that cloud computing is everywhere. A few people know that the data center is a key infrastructure of cloud computing. In this paper, we focus our attention on data center. Actually, data center, like cloud computing, is also everywhere. There are too many cloud providers run their data centers across the world. Among them, Amazon built data centers on 76 availability zones and serve more than 240 regions. Microsoft is another giant cloud provider, and it serves 140 countries. Data center network, also known as DCN, is responsible for connecting the servers in the data center. In the early days of cloud computing, a data center has tons of servers, and a switch can connect all of them. Later, with the increase of servers in a data center, hierarchical networks are used to connect hundreds of servers. As data center traffic grows quickly and more service providers deploy their applications on cloud platforms, data centers are getting bigger. Hundreds of thousands of servers are deployed in one data center. The explosion of traffic creates demand for more advanced data center networks. Some novel and complicated DCN architectures are proposed. Tree is one of them. It is a hierarchical and multi-root DCN architecture and has good scalability. It can support k-cubed servers with k-squared commodity switches. For a pair of racks not in the same port, there are several equal cost paths can be used. Tree delivers flows in randomly selected routing path named ECMP. As mixed traffic, including large flows and small flows, coexist in data center networks. Large flows have large size and generally have long durations, while small flows are small sized and expect low delay. They have different characteristics and requirements. Random routing schemas such as ECMP may send many large flows to one output port, generating queue. When small flows arrive after large flows, they join the queue and experience long delay, which is not consistent with small flows expectations and hurts users' experience. Besides that, all the cross-port traffic should flow through core layer switches, greatly increasing the load of DCN and affecting the flow performance. Here, we summarize the limitations of existing DCNs. In addition to the inefficient routing schema, conventional data center networks adopt deterministic and symmetric topologies, which is not able to handle the dynamic and unbalanced data center traffic well. Most of the existing DCNs are wire-based. Data center operators need to solve the complex wiring and difficult maintaining problems, which is costly. In this context, researchers turn to new architecture design. Researchers propose reconfigurable DCNs to solve the shortcomings of conventional wired DCNs. The main idea of reconfigurable DCNs is to use wireless techniques to augment DCNs, such as 60 gigahertz wireless free space optics and optical circuit switch. Then DCNs can achieve full flexibility and gigabit per link capability at low cost. There are some representative reconfigurable DCNs such as Flyway, 3D beamforming, and Firefly. Here I will give a motivating example to show the advantages of reconfigurable DCNs in augmenting flow performance. Let's look at the simple factory-based DCN. There are only wired links. In order to transfer large flows and small flows represented with red and green blocks from one rack to another rack in the side port, all data have to be flowed through core layer switches. It is easy to generate hotspots and affect the flow performance, especially small flows. That's not efficient. With wireless radios equipped on the top of rack, racks on different ports can communicate with direct wireless links without going through upper layers. We build a wireless link between the source rack and the destination rack that use wireless to transfer large flows and use wired links to transfer small flows. As large flows no longer compete with small flows and they are transferred with shorter links, both of small flows and large flows benefit. We want to improve flow performance in DCNs with hybrid routing schemas, as it has 3 advantages. First, wireless links between racks can greatly shorten the path length and lower bandwidth consumption. Second, wireless links can be dynamically built and removed. Operators can reconfigure wireless topology according to traffic demand easily and quickly. Load balancing as a desirable feature of DCNs can be easily achieved under the circumstances. Third, small flows and large flows have different properties and needs. Hybrid routing can treat them differently by taking into account their real needs. I just introduced why we want to design hybrid routing in reconfigurable DCNs. Here, we analyze the flows in real DCNs. We take flows larger than 100 kbytes as large flows and the remaining ones as small flows. We find that the top 10% large flows account for more than 60% of the total traffic volume, which is consistent with existing studies. Moreover, the arrival rate of small flows is much higher than that of large flows. Based on the characteristics collected from our analysis, our basic idea is to schedule large flows with hybrid routing and small flows with default routing strategies such as ECMP. As the number of large flows is small but their volume is high, by carefully scheduling large flows, we may get high profit. We want to model the hybrid routing optimization problem with the consideration of wireless interference and addressing it with good performance guarantee. In this paper, we take 60 GHz wireless as an example, as it is more complicated than FSO and OCS, but our solution can be used to solve the routing problems in other DCNs, such as FSO augmented DCNs and OCS augmented DCNs. 60 GHz wireless has some features such as high bandwidth, low power consumption, license-free, directional, and steerable. These features attract data center operators, while short-distance transmission and dense interference force operators to carefully use it. This is our problem formulation. The optimization objective is to minimize the maximal link utilization, which is a desirable feature of DCNs. We consider the wireless interference constraints, link capacity constraints, flow conservation constraints, and flow unsplittable constraints. By reducing the integer partition problem to our problem, we prove that the P0 problem is NT-hard. We first decompose our problem into two subproblems by relaxing unsplittable flow constraints and removing the wireless interference constraints. The first subproblem is to find the optimal site of interference-free wireless links, named the independent site or IS, and the second one is to find the optimal routing path for flows. We show that if we can approximately solve the two subproblems, we can approximately solve the original problem. Next, we will try to solve the subproblems with high performance. We propose an algorithm VLS to determine the interference-free independent site. In the solution space, there are a lot of integer s. Our goal is to find the optimal one. We first relax the integer s constraints to fractional ones. Then we approximate the solution space and improve the approximation ratio mu. Then we use convex decomposition and randomized rounding techniques to determine an S as the final one. The figure in the lower right shows the mu approximated convex hole and how to do convex decomposition. Suppose the optimal fractional solution S equals to the weighted sum of the four integer S, S1, S2, S3, and S4. The weights are alpha 1, alpha 2, alpha 3, and alpha 4. Through randomized rounding, we take the weight of each solution as the probability of selecting it as the final S. Here, we propose VLS to schedule flows on the topology determined by VLS. We decompose each flow into multiple passes and calculate the weight of each pass by pass stripping. Then we take the weight as probability to select one pass for each flow with randomized rounding. we prove the approximation ratio of the original problem by combining the approximation ratios of VRS and VRS. We also design an online solution to solve the aforementioned optimization problem, considering more practical factors. We propose two algorithms, FLS and FRS, to solve the problem. We take into account the reconfiguration cost when designing an online solution. Since it schedules arrived flows online, an optimal solution may introduce the updates of wireless links and the topology reconfiguration, which will affect the in-transit flows. We define it as reconfiguration cost and quantify it in the modified objective. In fast link setter, in each time slot, we first sort flows according to their size, and in descending order, we find the k shortest passes for each flows and try to shorten the transmission path length with available wireless links. After determining the wireless links, we use fast route scheduler to optimize the modified optimization objective, which takes into account the reconfiguration costs. The routing schema is similar to the VRS, which uses path stripping and randomized rounding to determine routing paths for each flow. In order to measure the 60 GHz wireless, we build a test bed and measure the wireless under different scenarios. Based on the obtained data, we compare our solutions with existing ones. Here shows parts of the evaluation results. Under different flow arrival rates, throughput of large flows increased by up to 99%. Flow completion time decreased by up to 72%. Under different traffic patterns, completion time of large flows decreased by up to 72%. Completion time of small flows decreased by up to 64%. We scale up a certain percent of flow sizes to simulate heavy network load and evaluate the performance of solutions. Handling data center hotspots. Compared to other schemes, throughput of Vero is up to 90% higher, and its flow completion time is up to 71% lower. We set different values for K and W, which represent the number of shortest paths that FLS searches and the weight of reconfiguration cost in FRS. Except when K equals 0, the average path length increases with the value of K. When W is very large, the flow scheduler will try to avoid rerouting to lower the optimization objective. Now, let's summarize this paper. In this paper, we propose two solutions to achieve efficient routing in reconfigurable DCNs. We aim to fully use the stable wired links and flexible wireless links. We jointly consider the interference and routing issues in our problem formulations. Our solutions can be easily extended to work with different wireless technologies. As cloud services and network scale are growing fast, improving the flow processing speed of our solutions is a new direction. That's all. Thank you for listening.